Hello friends, in this lecture we continue our discussion on solving time-independent Schrödinger equation to get energy eigenvalues and eigenfunctions in a 1D lattice. We have to solve the time-independent Schrödinger equation where U of x is an effective one-electron potential having the periodicity of the lattice. According to Bloch theorem, the eigenfunction is a plane wave times some function u of x, which has the periodicity of the lattice. However, u of x is a generic function and thus we do not know the exact form of psi of x. We also do not know the energy eigenvalues. In the previous lecture, we expanded ux in this form where G is reciprocal lattice point. Replacing u of x in time-independent Schrödinger equation, we rewrite in this form. However, we cannot solve it yet. We need to express psi of x also in the form of a Fourier series. Let us do that. For potential, we wrote the Fourier series of ux using the reciprocal lattice points or G points. Similarly, I claim that we can expand psi k of x, the wave function, in this form, where k can be any allowed k point. For example, we can take this point k2. G is a reciprocal lattice point. Since there is a sum over G, we have to consider all the terms which differ from k2 by G. For example, we have to consider k2 minus b, we have to consider k2 minus 2b, we have to consider k2 plus 2b, etc. This is an alternate form of Bloch theorem. We can accept psi k of x to be a solution of electron in a periodic potential provided psi k of x satisfy both Bloch theorem and periodic boundary condition. Let us verify that. Let us rewrite psi of x by bringing e power ikx outside the sum because the sum is over G. The term sum over G ck minus G e power minus igx. Let us rewrite this as uk of x such that we can write psi k of x as e power ikx uk of x. Now, this will look exactly like Bloch theorem provided uk of x has the periodicity of the direct lattice. Let us prove that ux plus na is equals to u of x, where n is some integer and a is spacing between adjacent direct lattice points. We write uk of x is equals to sum over G ck minus G e power minus igx. Now we try to find out uk of x plus na, and this is equal to sum over G ck minus G e power minus ig. So in place of x, I am going to replace x plus na. And this is equal to sum over G ck minus G e power minus igx into e power minus ig and a. Now note that G is equals to 2 pi m by a. If we replace it in this equation, then we get sum over G C k minus g e power minus igx e power minus I 2 pi m n. Now, since m is an integer and n is an integer, this term is equals to 1. Thus, we get this is equal to uk of x, right? So, we prove that uk of x is equals to uk of x plus na. Thus, this function uk of x has the periodicity of the direct lattice. Now that we have proved psi k of x satisfy Bloch theorem, let us also verify whether it satisfies the periodic boundary condition. Now, psi k of x is equals to sum over g c k minus g e power I k minus g times x. Now let us write psi k of x plus na. This is equal to sum over g c k minus g e power I k minus g, and in place of x I just write x plus capital N A. And this is equal to sum over g c k minus g e power I k minus g times x, and this term is nothing but psi of x, and then we have e power I k na times e power minus I g na. Now we know that k is equals to 2 pi n divided by na, and g is equals to n times 2 pi by a. If we replace k and g in this equation, then this term is equal to 1 and this term is equals to 1. And then that gives us the proof that psi k of x plus na is equals to psi k of x. Thus, psi kx also satisfies periodic boundary condition. Like we did for the potential, let us understand Fourier series expansion of psi of x using a simple Python code. For simplicity, let us keep only two terms in the Fourier series expansion. We take a k point in the first Brillouin zone, k1. For example, this point. The other k point, k2, is equals to k1 minus 2 pi by a. This means k2 is located here. Let us take the constants ck1 and ck2 to be equal. That is, ck1 is equals to ck2 is equals to 1 by square root of 2. In the code, the constants are defined here. We take an allowed k point. K is equals to 2 pi by 5 as shown here. In the diagram, this is the k point. This point lies in the first Brillouin zone, which is marked by the magenta shaded region. The other k point, k2, is k1 minus 2 pi. Note that I have taken the distance between two adjacent direct lattice points to be equal to 1. In the diagram, the second K point lies here. And this is outside the first Brillouin zone. The real part of the complex wave function contains cosine terms and defined here. The imaginary part of the complex wave function contains sine terms and defined here. Plotting real and imaginary part separately, we can verify the periodicity. For the complex wave function to be periodic, both real and imaginary part should be periodic. In this code, we plot the real and imaginary part here. Then we plot mod psi of x squared, which tells us whether the wave function satisfies Bloch theorem or not. In the code, we plot mod psi x squared here. This is the code to plot real and imaginary part of psi as well as probability density. Length of the periodic box is equal to 10 as shown here. We take K1 is equals to 2 pi by 5, which is one of the allowed K points obtained from the PVC applied on a box of length L equal to 10. K1 lies in the first Brillouin zone. The other point K2 differs from the point K1 by a reciprocal lattice vector 2 pi. This is where the real part and the imaginary part of the wave function is defined. This is where we plot the real part, this is where we plot the imaginary part, and this is where we plot the probability density. Let us run the code. The solid red line is the real part of the complex wave function, and the solid blue line is the imaginary part of the complex wave function. The dashed blue line is the probability density. Vertical red dotted lines show the location of the lattice points. Let us try another set of K values. In this case, we take K1 is equals to 2 pi by 5, same as before. And we take K2 is equals to 3 pi by 5. Note that K1 and K2 are just adjacent allowed K points. They are not separated by a lattice vector, unlike we did for the previous case. Now let us run the code. Remember that the solid has a length of L equal to 10 and distance between two adjacent points in real lattice is equal to 1. Thus, the direct lattice points are located at 0, 1, 2, 3, 4, etc. as shown by the vertical red dotted line in the diagrams. First, let us analyze the first diagram from the left, that is this one. The real and imaginary part of psi satisfies periodic boundary condition. By this, I mean that real and imaginary part of the wave function as well as its first derivative is continuous at x equal to 0 and at x equal to 10. At x equal to 0, this is the real part and this is the imaginary part of the wave function. At x equal to 10, this is the real part and this is the imaginary part of the wave function. Clearly, the wave function and its first derivative is continuous at the boundary. Moreover, probability density is equal at each lattice point, as shown in the diagram. This is the necessary condition for the wave function to satisfy Bloch theorem. Next, let us analyze the second diagram. The wave function satisfies the periodic boundary condition. Note that both real and imaginary part of the wave function as well as its first derivative is continuous at the boundary. For example, this is the real part of the wave function at the boundary, and this is the imaginary part of the wave function at the boundary. However, the probability density is not same at every lattice point. The probability density is maximum at the boundary and it decreases continuously as we move inside the solid. Thus, although the wave function satisfies periodic boundary condition, it does not satisfy Bloch theorem. So, this one cannot be a valid Bloch function. In conclusion, for psi of x to satisfy Bloch theorem, we need to do a Fourier series expansion of psi of x using allowed k points which differ from each other by some reciprocal lattice vector. Any other choice, for example, adjacent values of allowed k points, produce a wave function which satisfies periodic boundary condition but does not satisfy Bloch theorem. Now that we have learned how to expand the potential u and the wave function psi in a Fourier series, let us learn how to solve time-independent Schrödinger equation for Bloch electrons. So we are trying to solve time-independent Schrödinger equation for a potential having the periodicity of the 1D lattice. This is the Fourier series of the potential and this is the Fourier series of the wave function. G is a reciprocal lattice point and K is an allowed K point given by the periodic boundary condition. Using Python codes, we have verified that if we expand in this way, u of x has the periodicity of the lattice and psi of x satisfies periodic boundary condition as well as Bloch theorem. Let us substitute the Fourier series of u and psi in time-independent Schrödinger equation. Let us take only two terms in the expansion of u of b and u of minus b. That means these 2 points, b and minus b. U naught gives some constant potential in the direct lattice and we can set it to equal to 0. Because of symmetry, we can just take u of b and u of minus b to be equal. In case of psi, we take some allowed k point in the first billowing zone. For example, say this point. In the expansion of psi of x, terms like k minus b, that means if we take this point, then this term, and then the terms like k minus 2b and k plus 2b, etc. will enter. There are infinitely many terms and we show only a few here. Now, let us put psi of x and u of x in time-independent Schrödinger equation. We do it term by term, starting with this term. So, minus h cross square by 2m d2 dx square, and we put ck e power ik x plus we put the potential term u e power I bx plus u e power minus I bx times ck e power ikx is equals to epsilon times ck e power ik x. Now we have, so if I take derivative twice of this term e power I kx, we just get h cross square k square by 2m ck e power I kx plus u ck e power I k plus b x plus the second term u ck e power I k minus b x is equal to epsilon ck e power I k x. And this term h cross square k square by 2m, we just call it lambda of k, such that we can write the equation as lambda of k ck e power I k x plus u ck e power I k plus b x plus u ck e power I k minus b x is equals to epsilon ck e power I k x. Similarly, for this term ck minus b e power I k minus bx, we get this equation. And for the last term ck plus b e power I k plus bx, we get this equation. Thus, substituting Fourier series of ux and psi of x in time independent Schrödinger equation, we get these equations. I have shown for 5 terms in Fourier series of psi of x. So this is the first term and this is the corresponding equation. This is the second term and this is the corresponding equation. Third term, the corresponding equation. Fourth term and the corresponding equation. Fifth term and the corresponding equation. I have marked terms containing the components of e power I k minus bx in blue and e power I kx in red and e power I k plus bx in green. Why we are doing this? Because each component of the Fourier series must have same coefficient in both sides of the equation, and we are going to separate them in the next slide. Thus, we have 5 equations. Let us collect all the components of e power I k minus b times x from these 5 equations. So from equation 1, we have this term u c k minus 2b. From equation 2, we have 2 terms, this and this. And from equation 3, we have these terms u times ck. Note that e power I k minus bx does not have components like c k plus b and c k plus 2b. Thus, we write them as 0 times ck plus b and 0 times ck plus 2b. Similarly, we can collect all the components of e power I kx and then we get this equation, and we can collect all the components of e power I k plus b times x and then we get this equation. Collecting components of e power I k minus bx, e power I kx and e power I k plus bx, we get a system of linear equations as shown here. We can express the system of linear equations in the form of a matrix as shown here. Note that there are some non-zero terms in the first row and in the last row of the matrix as well. I leave it as an exercise for you to complete the first and last row of the matrix. Now, the solution of the determinant gives the energy eigenvalues of the Bloch electrons. Let me quickly summarize the most important steps for solving time-independent Schrödinger equation in case of Bloch electrons. First, we write the Fourier series expansion of u of x and psi of x in this form. Using Python codes, we have verified that if we expand in this way, u of x has the periodicity of the direct lattice and psi of x satisfies both periodic boundary condition and Bloch theorem. Putting the Fourier series expansion of u of x and psi of x in time-independent Schrödinger equation, we convert time-independent Schrödinger equation to a system of linear equations. Solution of the determinant gives the energy eigenvalues.